Hello, welcome to Chapter 13, Section 3, Radian Measure. Today we're talking about radians, okay, which is a unit of measurement that we're going to be using a lot, all right, and it actually doesn't have a unit, it's just radians. All right, so a central angle of a circle is an angle with a vertex at the center of a circle. An intercepted arc is the portion of the circle with endpoints on the sides of the central angle and remaining points within the interior of the angle, so what you see. Okay, it's not that complicated. When a central angle intercepts an arc that is the same length as a radius of the circle, the measure of the angle is defined to be 1 radian. All right, so when the radius is equal to the measurement of the arc. Because the circumference of a circle is 2 pi r, there are 2 pi radians in any circle at all. Now, we normally like to talk about a unit circle, but it doesn't have to be. 2 pi radians is 360 degrees, right, because that's how long it takes to get all the way around a circle. So pi radians equals 180 degrees, and that's what we're going to be using as a conversion unit. All right, so if we want to find the radian measure of an angle of 45 degrees, we need to take 45 degrees, all right, and you can technically put anything over 1, and we're converting it. So we're going to use the idea that 180 equals pi radians. Okay, 180 equals pi radians, which means that if I want to cancel out degrees, I need to put that in the denominator because I have degrees in the numerator on the first fraction. So 180 will be down here, and that's equal to pi radians. So I'll put pi in the numerator. Well, if that's the case, then I can just simplify 45 and 180. Well, the 45 goes into 180 4 times. So that's a 4 and that's a 1, which means I just have pi over 4. So 45 degrees is equal to pi over 4 radians. I can find the degree measure of an angle of 13 pi over 6 radians. So I start with 13 pi over 6, and I'm using the idea that pi radians is equal to 180. So I want pi to cancel out pi, which means I'm going to put it in the bottom. And 180 will go in the top, and that's in degrees. So the pi's will cancel. The 6 goes into 180 30 times. And then 13 times 30 is 390. So that is the same thing as 390 degrees. Let's do this again. More examples. Now we want to find the degree measure of an angle of negative 3 pi over 2 radians. So we have negative 3 pi over 2. And we want that to be in degrees, so we're going to use the conversion unit, that pi and 180 go over each other. But I want pi to be at the bottom, because if pi is at the bottom, then it'll cancel this pi right here. Okay, but I can't forget the 180 on the other side. Now that's in degrees, so 180 and 2, well 2 goes into 180 90 times. So we end up with negative 3 times 90, which is negative 270. So it's negative 270 degrees. If I want to find the radian measure of an angle of 54 degrees, then I'm going to do the same thing that I did in example 1, part A. I have 54 degrees. I can put anything over 1, right? I'm always allowed to do that. Now I'm still going to use the conversion. Pi is 180. And then 180 would go in the bottom. And pi would go in the top because I needed my degrees to be on opposite parts, right? I need one to be in the numerator, one to be in the denominator. That way the degrees cancel out. Now, if I try to simplify this, I can divide by, 9 or 18. Let's divide by 18. 18 goes into 54 3 times, and 18 goes into 180 10 times. So we end up with 3 pi over 10 radians. All right, and that's what we're doing. Now, if I ask you to find the exact values of cosine of pi over 3 and sine of pi over 3, we end up doing what we did in chapter 13, section 2. But I haven't shown you how to do that, so we're going to take it and convert it to degrees. So if I have pi over 3, and I need to turn it into degrees, I'm going to put pi on the bottom and 180 on the top, which will cancel this. 3 goes into 180 60 times, so 60. So we end up with 60 degrees. All right, so let's go to our graph. We'll use the unit circle. 60 degrees is going to be something like, it's going to be not that, but I'm just drawing a picture for help. All right, so this is 60 degrees, which means this is 30. All right, and I know that's where 60 is going to be ish, because that's the quadrant that 60 degrees is in. All right, so if I want to use my special angles, I know that this is 1 and that is s. This ends up being s root 3. And this ends up being, oh, this is s. This is 2s. All right, so if 2s equals 1, then s equals 1/2. Right, so this is just 1/2. And if s root 3 is, well, that means that if I plug in s for s root 3, we end up with root 3 over 2, because it'd be root 3 times 1/2. Don't forget, from last time, cosine is the x, so this is going to be cosine, and this is going to be sine, right? So cosine of pi over 3 is going to equal 1/2, while sine of pi over 3 is going to equal root 3 over 2. Okay? Now, dealing with length of an intercepted arc. For any circle of radius r and a central angle of measure theta, we're going to call our angles theta. All right, that's the Greek symbol for an angle. Okay. The length s of the intercepted arc is s equals r times theta, where r is your radius, right? We just said that. So we're going to use this idea to find the length s to the nearest tenth. Now s is actually this outer blue shell from 0 to there. All right, and I know it's not already written, but the angle here is 7 pi over 6, and this distance here is 6 inches. All right, so if we want to use that formula, s is going to equal the radius times theta. Well, they give us the radius. They told us it was 6. Theta is given by the angle, which was 7 pi over 6. And 6 and 6 cancel, so s just ends up equaling 7 pi. And for this case, we actually want it to be a little bit more practical to find the actual length instead of having it in terms of pi. So that ends up being, if you put that into your calculator, 21.99 inches. Right, and that's just putting 7 pi into your calculator. All right, let's do one that's a little more, even a little bit more work. Okay. All right, so let's answer this real-world question. A satellite completes one orbit around Earth every 4 hours. The satellite orbits 6,400 kilometers above Earth's surface. How far does the satellite travel in 1 hour? Well, additionally, another problem gave us that the radius of Earth is 6,400 kilometers, okay? And I did not expect you to know that. I would always give that to you. Well, since it completes one orbit every 4 hours, right, because it says a satellite completes one orbit around Earth every 4 hours, and we're trying to figure out how far the satellite travels in 1 hour, then we can predict that it would complete a quarter of an orbit every hour. All right, so it'll make its way a quarter of the way around the Earth in an hour. All right, so we really want to find S when when theta is a quarter of the whole distance all the way around the Earth. So when it's a quarter of 2 pi, because it takes 2 pi to get all the way around the Earth. So theta is going to be a quarter of the total distance all the way around the Earth, which is 2 pi. So that angle is going to be pi over 2. Now the radius is going to be the Earth's radius, right? So this, which is 6,400, and the distance that the satellite orbits above Earth's surface. So that distance, which also happens to be 6,400. Well, that means that the radius is 6,400 plus 6,400, which equals 12,800. And then we just use the formula. So the measurement of that arc is going to be, so how far does the satellite travel? So that's the measurement of the arc, is going to end up being theta, which was pi over 2, times your radius, which was 12,800. You put that into your calculator. Well, we simplify it first, right? Because we're dividing by 2. It's 6,400 pi. You put that into your calculator and you get 20,106 kilometers. Okay, and there's some practical application for what we're doing today. See you in class.